MIT6004 students work around the dryer bottleneck by finding a laundromat that has 2 dryers for every washer. Looking at the timeline, you can see the plan, which is divided into 30-minute steps. The washer is in use every step, producing a newly washed load every 30 minutes. Dryer usage is interleaved, where dryer number 1 is used to dry the odd-numbered loads, and dryer number 2 is used to dry the even-numbered loads. Once started, a dryer runs for a duration of 2 steps, a total of 60 minutes. Since the dryers run on a staggered schedule, the system as a whole produces a load of clean, dry laundry every 30 minutes. The steady-state throughput is 1 load of laundry every 30 minutes, and the latency for a particular load of laundry is 90 minutes. And now here's the take-home message from this example. Consider the operation of the 2-dryer system. Even though the component dryers themselves aren't pipelined, the 2-dryer interleaving system is acting like a 2-stage pipeline with a clock period of 30 minutes and a latency of 60 minutes. In other words, by interleaving the operation of 2 unpipelined components, we can achieve the effect of a 2-stage pipeline. Returning to the example of the previous section, we couldn't improve the throughput of our pipeline system past 1/8 nanoseconds because the minimum clock period was set by the 8 nanosecond latency of the C module. To improve the throughput further, we either need to find a pipeline version of the C component or use an interleaving strategy to achieve the effect of a 2-stage pipeline using 2 instances of the unpipelined C component. Let's try that. Here's a circuit for a general-purpose 2-way interleaver, using, in this case, 2 copies of the unpipelined C component, C0 and C1. The input for each C component comes from a D latch, which has the job of capturing and holding the input value. There's also a multiplexer to select which C component output will be captured by the output register. In the lower left-hand corner of the circuit is a very simple 2-state FSM with 1 state bit. The next state logic is a single inverter, which causes the state to alternate between 0 and 1 on successive clock cycles. This timing diagram shows how the state bit changes right after each rising clock edge. To help us understand the circuit, we'll look at some signal waveforms to illustrate its operation. To start, here are the waveforms for the clock signal and our FSM state bit from the previous slide. A new X input arrives from the previous stage just after the rising edge of the clock. Next, let's follow the operation of the C0 component. Its input latch is open when FSMQ is low, so the newly arriving X1 input passes through the latch, and C0 can begin its computation, producing its result at the end of clock cycle number 2. Note that the C0 input latch closes at the beginning of the second clock cycle, holding the X1 input value stable even though the X input is starting to change. The effect is that C0 has a valid and stable input for the better part of 2 clock cycles, giving it enough time to compute its result. The C1 waveforms are similar, just shifted by 1 clock cycle. C1's input latch is open when FSMQ is high, so the newly arriving X2 input passes through the latch, and C1 can begin its computation, producing its result at the end of clock cycle number 3. Now, let's check the output of the multiplexer. When FSMQ is high, it selects the value from C0, and when FSMQ is low, it selects the value from C1. We can see that happening in the waveform shown. Finally, at the rising edge of the clock, the output register captures the value on its input and holds it stable for the remainder of the clock cycle. The behavior of the interleaving circuit is like a 2-stage pipeline. The input value arriving in cycle I is processed over 2 clock cycles, and the result becomes available on cycle I plus 2. What about the clock period for the interleaving system? Well, there is some time lost to the propagation delays of the upstream pipeline register that supplies the X input, the internal latches and multiplexer, and the setup time of the output register. So the clock cycle has to be just a little bit longer than half of the propagation delay of the C module. We can treat the interleaving circuit as a 2-stage pipeline, consuming an input every clock cycle and producing a result 2 cycles later. When incorporating an n-way interleaved component in our pipeline diagrams, we treat it just like an n-stage pipeline. So n of our pipelining contours have to pass through the component. Here, we've replaced the slow unpipelined C component with a two-way interleaved C' component. We can follow our process for drawing pipeline contours. First, we draw a contour across all the outputs. Then we add contours, ensuring that two of them pass through the C' component. Then we add pipeline registers at the intersections of the contours with the signal connections. We see that the contours passing through C' have caused extra pipeline registers to be added to the other inputs to the F module, accommodating the two-cycle delay through C'. Somewhat optimistically, we specified the C' minimum T clock to be 4 nanoseconds, so that means that the slow component which determines the system's clock period is now the F module, with a propagation delay of 5 nanoseconds. So, the throughput of our new pipeline circuit is 1 output every 5 nanoseconds, and with 5 contours, it's a 5 pipeline, so the latency is 5 times the clock period, or 25 nanoseconds. By running pipeline systems in parallel, we can continue to increase the throughput. Here we show a laundry with 2 washers and 4 dryers, essentially just 2 copies of the 1-washer, 2-dryer system shown earlier. The operation is as described before, except that at each step the system produces and consumes 2 loads of laundry. So the throughput is 2 loads every 30 minutes for an effective rate of 1 load every 15 minutes. The latency for a load hasn't changed. It's still 90 minutes per load. We've seen that even with slow components, we can use interleaving and parallelism to continue to increase throughput. Is there an upper bound on the throughput we can achieve? Yes. The timing overhead of the pipeline registers and interleaving components will set a lower bound on the achievable clock period, thus setting an upper bound on the achievable throughput. Sorry, no infinite speed up is possible in the real world.